Where did the elements beyond iron come from? If iron is the heaviest element that can be formed in the core of a star through nuclear fusion, where did the heavier elements beyond iron come from? Join us as we share what scientists know and what they're still trying to figure out about the formation of heavy elements. Unraveling the cosmic origins. Elements are like the building blocks of everything we see around us. They're the tiny particles that make up all the stuff in the universe. Think of them as the alphabet of the universe. Just like letters combine to form words, elements combine to form compounds. But here's the thing. Elements themselves can't be made from something else. So, where did they all come from? Well, it all started with a colossal event called the Big Bang, which happened about 13.7 billion years ago. In the earliest moments after the Big Bang, a remarkable process called nucleosynthesis unfolded. This process marked the birth of atomic nuclei, the central cores of what would eventually become the very first atoms. However, these nascent nuclei were not yet complete atoms. They existed as charged entities, primarily protons, devoid of any orbiting electrons. During this swift nucleosynthesis phase, occurring mere minutes after the Big Bang, only light nuclei were formed. Approximately 75% consisted of single protons or hydrogen nuclei, while the remaining 25% were helium nuclei, composed of 2 protons and 2 neutrons. A smattering of other isotopes also emerged, but in tiny quantities. The nucleosynthesis period concluded when the universe was a mere 20 minutes old, leaving behind predominantly hydrogen and helium nuclei. Yet, from these elementary nuclei emerged all the diverse atoms we know today. But how did this transformation occur? Following the initial 20-minute period, the universe underwent a significant cooldown, from around 5 billion Kelvin to about 3,000 Kelvin, a process spanning roughly 380,000 years. During this phase, known as recombination, the universe reached a temperature where nuclei could capture electrons, forming neutral atoms instead of floating charged nuclei and electrons in a plasma state. Before this, the energy levels were too high for electrons to remain bound to nuclei. Thus, the first atoms emerged in the universe, although initially only the first 2 elements of the periodic table, hydrogen and helium, dominated the cosmic landscape. Yet there remained a puzzle, accounting for the remaining 96 naturally occurring elements. This is where the era of recombination comes in. Following this critical juncture, the universe plunged into darkness, devoid of stars. However, as hydrogen gas coalesced to form the universe's inaugural stars, the cosmic darkness gave way to the light of stellar fusion. Stars, the cosmic engines of light, owe their brilliance to the fusion process. In these stellar furnaces, hydrogen atoms meld together to form helium atoms, a process initiated in the star's scorching cores, where temperatures and pressures reach the requisite levels for fusion. This fusion process yields not only helium, but also releases energy in the form of heat and light. To delve deeper into this process, one can explore detailed explanations, such as those found in instructional videos illustrating how fusion unfolds in stars like our own Sun. Simplified, the fusion dance begins with 4 hydrogen atoms. With the aid of the weak force, capable of converting protons into neutrons, pairs of hydrogen atoms merge into deuterium, an isotope of hydrogen with an additional neutron. Subsequently, additional hydrogen nuclei fuse with deuterium to yield helium-3, an isotope of helium with only 1 neutron. These helium-3 atoms can then combine, liberating the borrowed protons and forming stable helium-4 atoms. Throughout this fusion cascade, energy is unleashed, further fueling the stellar brilliance illuminating the cosmos. This fusion process isn't limited to just a few steps. It's an ongoing journey toward crafting heavier and more complex atoms. Now, you might have thought that the Sun, in its luminous glory, single-handedly created all the elements we find in the universe through this fusion magic. But, oh, it's a tale far more complex than that. Our Sun, though a radiant star in its own right, has its fusion limitations. It can only carry on this atomic alchemy until it reaches elements like carbon or nitrogen. Why the sudden halt, you ask? It all boils down to energy. Fusion of hydrogen packs a punch of energy. But as the elements grow heavier, the energy output dwindles. A star is like a cosmic warrior locked in a fierce battle. On one side, there's the relentless pull of gravity, seeking to crush the star inward. On the other, there's the fiery rebellion of radiation pressure from fusion, pushing back against gravity's embrace, striving to keep the star from collapsing. It's a breathtaking tug-of-war between these cosmic forces. A delicate balance, keeping the star from tipping into oblivion. But alas, for smaller stars, the struggle becomes too much. They lack the fiery vigor needed to sustain the fight when forging heavier elements. Slowly, they succumb, collapsing into tiny white dwarfs, their once vibrant glow dimming into darkness. And thus, the fusion flame flickers and fades, leaving behind a silent void where once a star's brilliance lit up the cosmos. Now let's delve into the mysterious origins of heavy elements, those shimmering treasures beyond the familiar. Forging elements beyond iron. In the celestial saga, where stars, both big and small, play out their cosmic roles. The larger stars, the cosmic behemoths, have the power to push the boundaries further. As these colossal stars near the end of their cosmic journey, they become celestial forges, weaving a tapestry of elements within their core. The star's core can be likened to a grand workshop, with layers upon layers of elements being crafted. Closest to the fiery heart lies the heaviest nuclei, forged under immense pressure and scorching temperatures. As the elements grow lighter, they find their place closer to the surface, in the star's outer layers. But even for these mighty stars, there comes a point where the scales tip unfavorably. The energy required to fuse elements beyond iron outweighs the energy produced in the fusion process itself. Iron, with its mighty nucleus, stands as an impassable barrier. It holds onto its energy tightly, refusing to release any more. And so, the fusion furnace halts at iron's doorstep, and the stars meet their inevitable fate. Yet, it's astounding to think that within their cores, stars transform humble hydrogen into elements as far-reaching as iron. But what of the elements beyond iron? For that, we venture into the twilight of a star's life. When a massive star breathes its last, it goes out with a bang, a supernova. This cosmic spectacle, similar to celestial fireworks, lights up the heavens for a fleeting moment. But behind this brilliance lies a tale of cosmic collapse. As the star exhausts its fuel, its fiery breath fades. Gravity, the ancient force, tightens its grip, pulling the star inward with unimaginable force. In the blink of an eye, a titan collapses into a mere speck, unleashing shockwaves that ripple through the cosmos. It's in this cataclysmic chaos that the seeds of heavier elements are sown, including uranium. The extreme temperatures of a supernova forge elements beyond iron, creating a celestial abundance that defies imagination. Even the iron that adorns our Earth owes its existence to these cosmic fireworks. And so, from iron to zirconium, the periodic table finds its completion in the cosmic crucibles of exploding stars. It's a tale of grandeur and destruction, where stars birth elements that dance through the cosmos, enriching the tapestry of existence. And in this cosmic drama, smaller stars like ours play a quieter role, their humble glow lighting the way in the vast expanse of the universe. These modest stars, while they may not match the cosmic prowess of their larger counterparts, possess a remarkable ability. They can weave elements, up until the mighty nitrogen, within their cosmic looms. But as these stars near the end of their existence, a cosmic drama unfolds. Their cores, exhausted from the fiery dance of nuclear fusion, begin to collapse. It's a cosmic sigh as their once vibrant cores shrink, sending ripples through their outer layers. In this cosmic showdown, the stars swell into majestic red giants, their fiery embrace reaching out towards the heavens. In the eons to come, even our sun will join this celestial waltz, expanding to engulf the space that once cradled our Earth. And as its outer layers, enriched with elements like nitrogen, drift away into the cosmic winds, a silent sentinel remains. A white dwarf, a cosmic remnant, a relic of bygone eras. Although these stars may not birth elements heavier than nitrogen, they carry within them the echoes of cosmic alchemy. Born from the remnants of ancient stars, these stellar siblings contain elements beyond iron, and in their cosmic cauldrons, where fusion reigns supreme, they concoct a new recipe for cosmic creation, from neutron stars to stellar nurseries. Electrons and protons are squished together to form neutrons, creating a superdense object known as a neutron star. These stellar remnants are incredibly dense, with just a teaspoonful weighing as much as 500 million tons. Imagine two neutron stars colliding in the vastness of space, creating an explosion of unimaginable heat and pressure. This cosmic collision unleashes a torrent of free neutrons, with up to a gram of these tiny particles spilling into every cubic centimeter of surrounding space. In these extraordinary conditions, something incredible happens. The rapid neutron capture process, or R process, kicks into gear. It all begins with a humble nucleus, like iron, acting as a seed for the process. Normally, an iron nucleus has around 26 protons and 30 neutrons. But during the R process, it swiftly captures a multitude of additional neutrons in just milliseconds. This sudden influx of neutrons destabilizes the nucleus, prompting some of them to decay into protons. The result? A brand new form of matter is born in the chaos of this rapid and intricate process: gold. Despite the numerous elements listed on the periodic table, it's fascinating to discover that a whopping 98% of all the matter visible in the universe consists solely of two elements: hydrogen and helium. This means that the vast majority of what we can see, including the atoms within our bodies and on Earth, is essentially made up of just these two elements. The remaining 96 natural elements, including carbon, nitrogen, and oxygen, collectively make up a mere 2% of the visible matter in the universe. However, this small fraction is still significant, as it encompasses the elements crucial for life as we know it. Yet the prevalence of these elements doesn't necessarily imply that life is rare in the universe. While they may not be considered exotic, they are widely distributed throughout space. For instance, they can be found in nebulae, the cosmic nurseries, where stars like our Sun are born. It's within these stellar nurseries that planets, likely composed of the same set of elements found on Earth, are also likely to form. Therefore, if life is indeed sparse in the universe, it's unlikely to be solely due to a scarcity of exotic elements. It's equally fascinating to learn that the elements beyond iron aren't made inside stars like most other elements. Instead, they're formed through extraordinary cosmic events, such as supernovae. The universe is incredibly big and full of mysteries that go way beyond what we can even imagine. If we want to catch a glimpse of all these amazing things, we can dive into books and watch videos about astrophysics and cosmology. What are your thoughts on the mysteries of how the heavy elements were formed? Let us know your thoughts in the comments below.